Out there, in the frozen darkness beyond Neptune, drifts a world so strange, so utterly perplexing, that even the sharpest minds in astronomy can't fully unravel its secrets. Meet Varuna, an enigmatic relic from the dawn of our solar system, a cosmic puzzle wrapped in ice and shadow. Discovered just over 2 decades ago, this distant trans-Neptunian object defies expectations at every turn. It's not just another frozen rock in the Kuiper Belt. It's a gravitational oddity, a celestial anomaly that whispers questions we're still scrambling to answer. Why does it rotate so fast? What hidden forces shaped its bizarre, elongated form? And perhaps most chilling of all, what else is lurking in the abyss around it? Varuna isn't just a scientific curiosity, it's a gateway to the unknown. Named after the ancient Hindu deity of the cosmic waters, this distant world seems almost alive with mystery, as if it's daring us to uncover its truth. Imagine a place where sunlight is a faint memory, where temperatures plunge so low that even time feels frozen. Yet here, in this seemingly lifeless void, Varuna dances to its own rhythm, spinning faster than any object its size should, its surface scarred by forces we don't yet understand. Some researchers suspect it's a fragment of a much larger world, shattered in a cataclysmic collision billions of years ago. Others whisper about even stranger possibilities, hints of exotic ices, hidden subsurface oceans, or gravitational quirks that could rewrite what we know about the outer solar system. This video is your ticket to the edge of discovery, where every unanswered question pulls us deeper into the unknown. Over the next 25 mysteries, we'll peel back the layers of Varuna's secrets, from its unnerving speed to the eerie way it reflects light, as if something beneath its surface is watching us back. Each clue we uncover only leads to more questions, and by the end, you'll see why scientists are obsessed with this distant, haunting world. So buckle up. We're about to journey into one of the solar system's greatest enigmas, and trust me, what we find might just leave you questioning everything you thought you knew about the cosmos. Most worlds in the outer solar system move at a glacial pace, their rotations measured in days or even weeks. But Varuna, it spins like it's running from something. This distant, icy body completes a full rotation in just under 6 hours, blisteringly fast for an object nearly 700 kilometers wide. To put that into perspective, if Earth spun that quickly, our days would be a chaotic blur, with hurricanes raging non-stop as the planet strained to hold itself together. So how does Varuna pull this off without tearing itself apart? One leading theory points to a violent past. Imagine a colossal impact billions of years ago, a collision so powerful it sent debris spiraling into the void and left the shattered remnant spinning wildly like a top flicked by a cosmic finger. This could explain Varuna's elongated shape too, as if it were stretched by the sheer force of that ancient catastrophe. Some astronomers even speculate it might not be a single object at all, but a loose pile of rubble barely held together by gravity, its fragile structure allowing it to whirl at this reckless speed without flying apart. But there's another, more unsettling possibility. What if Varuna's spin isn't just a relic of destruction, but a clue to something hidden beneath its surface? Subsurface oceans, kept liquid by radioactive decay or tidal forces, could subtly shift its mass, acting like an unseen hand cranking its rotation faster. Or perhaps exotic ices, with properties we've barely begun to understand, behave strangely under the extreme cold and pressure of the Kuiper Belt, creating internal dynamics we can't yet model. Then there's the haunting question no one can fully answer. If Varuna's spin defies the rules, what else have we gotten wrong about the outer solar system? Every time we think we've unlocked one of its mysteries, this icy enigma reminds us the cosmos loves a good surprise. Most worlds massive enough to hold themselves together under gravity end up roughly spherical, nature's way of balancing forces into a stable, symmetrical form. But Varuna, it breaks the mold. This distant wanderer isn't a neat, compact sphere like Pluto or Eris. Instead, it's stretched, distorted, almost as if some unseen hand gripped it at both ends and pulled. Observations suggest an elongated, possibly egg-shaped structure, a cosmic oddity that shouldn't exist at its size. So why does Varuna look like it's been squeezed by the universe itself? The answer might lie in that dizzying spin we just explored. Picture a ball of dough flung onto a spinning potter's wheel. The faster it turns, the more centrifugal force stretches it outward. Varuna's 6-hour rotation could be doing the same thing, its equator bulging while the poles flatten under the strain. But here's the catch: most objects this large have enough gravity to resist such extreme distortion. That suggests Varuna's interior isn't just solid ice and rock. It might be fractured, porous, or even loosely packed, like a rubble pile barely holding its shape. Some researchers propose its core could be a labyrinth of caverns and cracks, left behind by that ancient collision thought to have set it spinning. Without a dense, cohesive structure, it would deform more easily, like a half-inflated balloon twisting in the wind. Then there's the wild card: tidal forces. If Varuna once had a close companion, a moon or binary partner, their gravitational tug-of-war could have stretched it over eons, leaving it permanently warped even after the other object drifted away. We've seen this with other Kuiper Belt binaries, where mutual orbits sculpt bizarre, peanut-like shapes. But here's where it gets eerie. Current surveys haven't found any moons around Varuna. If tides are the culprit, where's the evidence? Was its partner ejected, destroyed? Or are we just missing something hidden in the glare of its icy surface? The stakes are higher than they seem. Varuna's shape isn't just a curiosity, it's a window into the chaos of the early solar system. Every irregularity hints at a history of violence, collisions, close encounters, or conditions so extreme they defy our models. And if we're wrong about how objects behave this far from the Sun, what else might we be missing? The Kuiper Belt could be littered with deformed worlds, each a silent witness to forces we're only beginning to understand. One thing's certain: Varuna refuses to fit into any neat category. Its shape mocks our expectations, reminding us that out here in the frozen dark, the universe plays by its own rules. In the vast, sun-starved reaches of the Kuiper Belt, most icy worlds gleam like faint beacons polished by eons of cosmic radiation into reflective surfaces that bounce back what little light touches them. But Varuna, it's different. This shadowy outlier absorbs nearly all the sunlight that falls upon it, making it one of the darkest objects ever detected in the outer solar system. With an albedo, or reflectivity lower than fresh asphalt, its surface is a murky enigma. What could possibly cloak this distant world in such profound darkness? The answer might lie in the chemistry of its frozen crust. While typical Kuiper Belt objects are coated in bright ices like methane or nitrogen, Varuna's surface seems steeped in something far more sinister. Laboratory experiments suggest complex organic compounds, forged over billions of years by cosmic rays bombarding simple ices, could create a tar-like residue darker than crude oil. Imagine a world where sunlight triggers chemical reactions so slowly that each photon absorbed helps build an ever-thickening shroud of cosmic soot. Some astronomers even speculate about tholins, the same eerie, reddish-brown polymers found on Pluto and Titan, but in concentrations so dense they blot out almost all reflection. Then there's the chilling possibility of geological activity. Most dark surfaces in the solar system, like those on Saturn's moon Phoebe, are thought to be ancient and untouched. But Varuna's rapid spin and odd shape hint at internal heat, however faint. Could cryovolcanoes or geysers be spewing dark sludge from its depths, painting the surface in fresh layers of shadow? Or has micrometeorite bombardment pulverized its crust into a fine, light-swallowing dust like charcoal strewn across snow? The implications go beyond mere curiosity. A surface this dark absorbs more heat, however minimal enough to subtly alter Varuna's thermal evolution. It might explain the cracks and strains believed to warp its shape or even fuel that bewildering spin. And if such darkness isn't unique, our census of the Kuiper Belt could be missing countless shadow worlds, invisible to our telescopes not because they aren't there, but because they refuse to shine back at us. Varuna's blackened face is more than a scientific puzzle, it's a mirror showing us how little we truly know. Every beam of light it swallows is a question left unanswered, a reminder that even in the void, darkness finds ways to deepen. In the frigid depths of the Kuiper Belt, where sunlight is 1,000 times dimmer than on Earth, many icy worlds cling to fragile, transient atmospheres, whisper thin blankets of gas that freeze and thaw with the seasons. Pluto has its hazy nitrogen shroud, Eris may hoard pockets of methane vapor, even tiny Makemake shows hints of fleeting atmospheric activity, but Varuna, it stands utterly bare. Despite being large enough to potentially hold onto gases, its surface betrays no trace of an atmosphere, past or present. This absence isn't just puzzling, it's a glaring anomaly that challenges everything we know about how distant worlds behave. The first clue lies in temperature. Varuna orbits so far from the Sun that surface temperatures hover near -230 degrees Celsius, cold enough to turn most gases into solid ice. But that can't be the full explanation. Other objects in similar orbits, like Kuiper, manage to maintain tenuous atmospheres when they swing closest to the Sun. Varuna's lack of even these temporary exhalations suggests something fundamental is different about its composition. Perhaps its ices aren't the volatile types like nitrogen or carbon monoxide that easily vaporize. Instead, its crust might be dominated by heavier, more stubborn molecules, such as water ice mixed with rock, locking gases away in a permanent deep freeze. Then there's the matter of gravity. Varuna's mass, estimated at just 3% of Pluto's, creates a feeble gravitational grip, too weak to prevent gas molecules from escaping into space over time. But here's the twist. Calculations show it should still be capable of clinging to some atmosphere, however thin, unless, of course, its rapid spin plays a role. That dizzying 6-hour rotation might be flinging potential gases away like a child shaking water from a spinning umbrella, creating an invisible barrier where no atmosphere can take hold. But the most tantalizing and unsettling theory involves Varuna's violent past. If it truly is the remnant of a cataclysmic collision, that impact could have blasted away any primordial atmosphere it once possessed, leaving it permanently stripped. Worse, the heat from such an event might have chemically altered its surface, baking volatile ices into inert crusts that can no longer sublimate. It's as if Varuna was sterilized by trauma, its ability to breathe frozen away by ancient catastrophe. The implications are profound. If Varuna can't hold an atmosphere despite its size, we may need to rethink how we classify objects in the outer solar system. Atmosphere retention isn't just about mass and temperature, it's a fingerprint of history shaped by spin, chemistry, and violence. And if worlds like Varuna are more common than we thought, the Kuiper Belt could be far stranger and far quieter than our models predicted. A realm not of murmuring gaseous envelopes, but of silent, airless sentinels, keeping their secrets under endless night. Deep in the Kuiper Belt, where temperatures should be locked in deep, unyielding cold, Varuna plays by its own thermal rules. Unlike most distant icy bodies that maintain a near-constant chill, this shadowy world exhibits temperature swings so erratic they baffle astronomers. Infrared scans reveal patches of its surface warming unpredictably, not by much, maybe just a few degrees, but enough to defy the ironclad laws of thermodynamics governing objects this far from the Sun. What cosmic trickery could cause a world in perpetual twilight to flicker with these faint but measurable heat signatures? One possibility points to residual warmth trapped beneath Varuna's crust. While most Kuiper Belt objects froze solid billions of years ago, Varuna's rapid spin and odd shape suggest it might still cling to fragments of internal heat. Radioactive isotopes like potassium-40 or thorium-232, common in rocky bodies, could decay at a glacial pace, generating just enough energy to create subtle thermal pockets beneath the ice. Imagine a planet-sized thermos, so well insulated by its own frozen exterior that whispers of primordial warmth still seep through cracks we can't yet see. Then there's the tidal theory. If Varuna once had a moon, or still does, hidden from our telescopes, their gravitational dance could stretch and compress its interior like putty, generating friction heat. Europa and Enceladus owe their subsurface oceans to this very effect, but here's the catch: no such moon has been detected, unless, of course, it was ripped away by some ancient catastrophe, leaving behind ghostly tides that still agitate Varuna's core like a phantom limb. More puzzling still are the surface patterns themselves. The warm spots don't align with expected solar heating. They appear almost random, as if something beneath the ice is redistributing heat in ways our models can't predict. Could cryovolcanoes be at work, spewing slushy plumes that refreeze into temporary insulating blankets? Or does Varuna's dark, light-absorbing crust create localized hot zones where sunlight, however feeble, pools like ink blots? The most unsettling hypothesis involves external forces. Varuna's orbit isn't perfectly circular, it wobbles slightly, moving closer and farther from the Sun over centuries. Computer simulations show these subtle shifts shouldn't significantly affect surface temperatures. Yet recent data hints at a correlation between its orbital position and thermal spikes. This suggests something else is at play, perhaps interstellar radiation concentrated by magnetic fields we don't yet understand, or even dark matter interactions, though that remains firmly in speculative territory. What makes these fluctuations so tantalizing is what they imply about the broader Kuiper Belt. If Varuna isn't the ice-cold corpse we assumed, how many other distant worlds might harbor hidden warmth? And in the unimaginable cold of deep space, even a few degrees of variance could mean the difference between sterility and just maybe the faintest whispers of chemistry complex enough to blur the line between geology and biology. Varuna's temperature quirks aren't just scientific footnotes, they're cracks in our understanding, letting in slivers of light where we expected only darkness. Most objects in the Kuiper Belt follow a predictable script born from the swirling disk of ice and rock that once encircled the young sun. They've spent billions of years in quiet, icy solitude. But Varuna, its origin story reads more like a cosmic thriller, with astronomers hotly debating whether this strange world is a native of the outer solar system or an exiled wanderer from darker, more turbulent realms. The answer could rewrite everything we think we know about the Kuiper Belt's violent past. On one side of the argument are the traditionalists who point to Varuna's orbit as evidence of a local origin. It moves along a path typical of classical Kuiper Belt objects, those thought to have formed roughly where they now reside. Its composition, rich in water ice and organic compounds, matches other denizens of this frigid zone. But here's the catch: Varuna's extreme elongation and wild spin don't fit the profile of a sedately formed world. Most Kuiper Belt objects this size are spherical, their rotations slowed by time and collisions. Varuna behaves more like a refugee, something flung from chaos into the relative calm of the outer solar system. This leads us to the exile theory. Imagine the early solar system, a demolition derby of protoplanets and debris. Some models suggest Varuna may have originated closer to the giant planets, perhaps near Neptune, before gravitational kicks sent it careening outward. Its peculiar shape and spin could be scars from this violent ejection, like a bullet twisted by the barrel of a gun. Supporting this idea are subtle chemical quirks in its surface ices, which show ratios of isotopes slightly different from typical Kuiper Belt objects. It's as if Varuna carries a foreign accent in its molecular structure, hinting at a birthplace far from its current home, yet the plot thickens further. Some researchers propose a third, even more dramatic possibility, that Varuna isn't from our solar system at all. The same processes that supposedly flung Oumuamua and Borisov into interstellar space might have also stranded alien visitors within our own cosmic backyard. While no definitive proof supports this radical idea, Varuna's darkness, its strangely low reflectivity, bears an uncanny resemblance to some of the ultra-red objects observed in other star-forming regions. Could it be a captured interloper, frozen in place when our sun's gravity won a celestial tug-of-war billions of years ago? The stakes of this mystery couldn't be higher. If Varuna is a local, its bizarre properties force us to reconsider how Kuiper Belt worlds evolve. Maybe the outer solar system was far more violent than we imagined, with collisions common enough to leave survivors as misshapen as Varuna. But if it's an exile, or worse, an immigrant, then the Kuiper Belt isn't the pristine relic we thought. It's a cosmic junkyard filled with the wreckage of gravitational wars and interstellar drifters. Either way, Varuna's true origin hides clues not just about one strange world, but about the turbulent adolescence of every planet, moon, and asteroid we see today. Perhaps the most humbling thought: we may never know for certain. Without a spacecraft visit, without touching its surface or sampling its ices, Varuna's past remains a labyrinth of competing theories. And that's the beauty of it. This distant enigma keeps us questioning, keeps us dreaming, because in its icy silence lies a truth that could shatter our solar system's origin story, or confirm it in ways we never expected. Varuna's solitude is as puzzling as it is profound. In the Kuiper Belt, objects of its size almost always travel with companions. Pluto has Charon, Eris has dysnomia, even smaller worlds like Orcus and Quaoar boast detectable moons. Yet after decades of searching, not a single satellite has been confirmed orbiting this rapidly spinning oddity. For an object nearly 700 kilometers wide, this cosmic loneliness defies statistical odds. Where are Varuna's missing moons, and what does their absence reveal about this world's violent past? One possibility is that we simply haven't spotted them yet. The challenge of detecting Kuiper Belt moons can't be overstated. They're often just specks of darkness lost in the glare of their parent bodies, thousands of times fainter than the objects they orbit. Varuna's own coal-black surface makes the task even harder, as any potential moon would need to contrast against what might be the darkest backdrop in the outer solar system. Some astronomers speculate there could be tiny, irregular companions, perhaps just a few kilometers across, hidden in observational noise. The New Horizons mission's discovery of Ultima Thule's bizarre pancake moons proved how easily small, oddly shaped satellites can evade detection. But there's a darker, more dramatic explanation. Varuna's extreme rotation and distorted shape scream of past catastrophe, perhaps a collision so violent it stripped away any orbiting bodies. Computer simulations show that when two large Kuiper Belt objects collide, the debris can form temporary rings that quickly coalesce into moons. However, if the impact is glancing or particularly energetic, those moons might be ejected entirely, leaving behind only a scarred, spinning remnant. Picture two ice worlds meeting in slow motion, the force of their encounter ripping apart any existing satellites while simultaneously stretching the survivor into Varuna's current, elongated form. The numbers tell a haunting story. Varuna's spin rate is teetering on the edge of stability any faster, and centrifugal force would overcome gravity, potentially flinging surface material into space. This suggests any moons it once held would have faced brutal tidal forces, either spiraling inward to be shredded or outward to be lost forever. Other fast-spinning Kuiper Belt objects like Haumea show similar patterns. Its two tiny moons cling desperately close, survivors of what may have once been a larger system. Varuna's lack of even these tenacious satellites hints at an even more violent disruption, as if something literally knocked the world clean of companions. Yet the most intriguing theory involves an invisible present rather than a catastrophic past. Some models suggest Varuna could possess a diffuse, ephemeral ring system, not of solid moons but of countless icy particles trapped in orbital resonance with its rapid spin. Saturn's faint G-ring and Jupiter's wispy halo prove such structures can persist without a shepherd moon. If Varuna's debris field is porous enough, it might scatter light in ways our telescopes can't easily detect, creating the illusion of emptiness around the world. The implications stretch far beyond one oddball object. If Varuna truly lacks moons while similar-sized neighbors retain them, we may need to rethink how Kuiper Belt systems form and evolve. Current models assume most large objects acquire satellites through collisions or captures, but Varuna's existence suggests exceptions to these rules might be more common than we thought. Every search that comes up empty forces us to confront an uncomfortable truth. The outer solar system's history may be written not in the objects we see, but in the ghosts of those we don't. Perhaps future observations will unveil a faint companion hiding in Varuna's shadow, or perhaps its enduring solitude will stand as cosmic testimony to some ancient cataclysm too violent for moons to survive. Either way, the void around this spinning enigma speaks volumes, whispering of forces powerful enough to sculpt worlds while erasing their histories entirely. Imagine a world where time itself should have left the surface scarred and pockmarked, a celestial fossil bearing the wounds of billions of years of cosmic bombardment. That's what astronomers expected to find on Varuna, yet when observations peeled back its dark, enigmatic shroud, they revealed something startling, a surface suspiciously smooth with no large craters visible. For an object this ancient, that absence is louder than any impact. It's as if Varuna has been quietly erasing its own history. Crater counts are one of astronomy's most trusted clocks. In the airless, weatherless void of the outer solar system, impacts should accumulate like wrinkles on an aging face, each collision a permanent record of the past. Pluto's surface is a testament to this, its terrain a chaotic mosaic of overlapping craters. Even mid-sized Kuiper Belt objects like Kuiper show the expected peppering of ancient strikes. But Varuna, its darkness hides a face nearly unmarked by violence. Either we're witnessing something extraordinarily rare, a world that's dodged every major impact for 4.5 billion years, or forces we don't yet understand are somehow resurfacing it. The most straightforward explanation would be geologic activity. On icy moons like Europa and Enceladus, subsurface oceans and shifting ice sheets constantly renew the surface, erasing craters over time. Could Varuna harbor similar secrets? The idea seems far-fetched at first. This isn't a world heated by a giant planet's tides. But Varuna's bizarre spin and thermal quirks suggest it might cling to faint internal warmth, perhaps enough to soften its icy crust. Picture slow-motion landslides triggered by that rapid rotation, or cryovolcanoes oozing sludge that fills in impact scars over millennia. Even a trickle of geologic movement sustained over eons could explain the missing craters, like fresh snow gradually burying footprints in a field. Yet there's a darker, more unsettling possibility. What if the impacts are there just invisible to us? Varuna's surface is among the least reflective ever measured, absorbing nearly all light that touches it. Standard crater detection methods rely on shadows cast by crater rims, but on a world this dark, those shadows might blend seamlessly into the abyss. It's like searching for footprints on a pitch-black beach. The depressions exist, but without contrast they vanish into the void. Some researchers speculate that advanced radar imaging, of the kind used to map Titan's dunes, might reveal hidden craters lurking beneath the lightless facade. Or perhaps the answer lies in Varuna's strangest feature, its shape. Most cratering models assume spherical targets, but Varuna's elongated form would distort impact dynamics dramatically. A strike along its stretched equator might spread energy unevenly, creating shallower, more ephemeral scars. Add in the wild centrifugal forces from its spin, and ejected debris could rain back down in unpredictable patterns, partially filling craters as they form. It's the difference between tossing a rock into still water and hurling one into a churning whirlpool. The resulting splash tells entirely different stories. The implications ripple outward. If Varuna's surface is actively renewing itself, even sluggishly, it joins an exclusive club of worlds where geology defies expectations. But if its craters are simply lurking unseen, we may need to rewrite the rules for observing dark, distant objects. Either way, this absence speaks volumes, not just about one odd world, but about the hidden lives of all the frozen relics drifting in the Kuiper Belt's endless night. The silence of Varuna's unscarred face may be the most deafening clue yet. When astronomers point their spectrometers at Varuna, the data that comes back doesn't just defy expectations, it practically rewrites the rulebook. While most Kuiper Belt objects show spectral fingerprints dominated by familiar ices like methane, nitrogen, and carbon monoxide, Varuna's surface broadcasts a far stranger chemical signature. There are absorption lines in its spectra that don't neatly match any known compound in our solar system's icy inventory. It's as if this distant world is coated in something we've never seen up close, a cosmic cocktail that raises more questions than answers. One leading theory suggests the presence of irradiated complex organics. When simple ices like methane or ammonia are bombarded by cosmic rays over billions of years, they can polymerize into reddish-brown macromolecules called tholins, the same compounds that give Pluto its rusty hue and Titan its hazy orange sky. But Varuna's spectra go beyond even these exotic substances. Some researchers have detected hints of cyanide compounds and polycyclic aromatic hydrocarbons, molecules more commonly associated with interstellar dust clouds than with mid-sized Kuiper Belt objects. How did these materials concentrate here? One possibility is that Varuna formed in a particularly dense region of the primordial solar nebula, where ultraviolet radiation and particle fluxes were intense enough to bake these complex molecules directly into its crust. Then there's the tantalizing and controversial detection of what might be ammonia hydrates. These water-ammonia mixtures have spectral features that partially align with Varuna's puzzling data, and their presence would be a game-changer. Ammonia acts as an antifreeze, lowering the melting point of ice dramatically. If confirmed, it could mean Varuna's interior harbors pockets of slushy, semi-liquid brine even at its frigid orbital distance. The implications are staggering. Where there's liquid water and organic compounds, even in trace amounts, the boundary between chemistry and biology begins to blur. But the real shocker comes from recent observations suggesting possible metal oxides in Varuna's surface layer. Most Kuiper Belt objects are too small and cold to have undergone the geological processes that concentrate metals, yet here we are, looking at spectral lines that resemble weathered iron or manganese compounds. One radical explanation posits that Varuna might be the remnant core of a much larger body, one that was massive enough to differentiate before being shattered in an ancient collision. Imagine a Pluto-sized proto-world torn apart, leaving behind its metallic heart exposed to the vacuum of space, slowly rusting under cosmic radiation. The mystery deepens when we consider how these materials could persist. Varuna's rapid spin should theoretically blast loose surface molecules into space, yet its exotic coatings remain stubbornly in place. This suggests the compounds might be bound in some kind of stable, tar-like matrix, a cosmic equivalent of asphalt slowly curing in the darkness. Alternatively, ongoing cryovolcanic activity could be replenishing the surface, though no direct evidence of such processes has been detected yet. What makes Varuna's chemical enigma so compelling is what it implies about the diversity of the outer solar system. If one mid-sized Kuiper Belt object can harbor such unusual compounds, how many other chemical oddballs might be lurking in the darkness? Each strange absorption line in its spectrum is a breadcrumb trail leading us toward a startling realization. The building blocks of our cosmic neighborhood may be far more varied and far stranger than we ever imagined. Varuna's density tells a story that doesn't add up, at least not by the usual cosmic rules. When scientists crunched the numbers, expecting something akin to Pluto's solid, rocky ice mix, they got a curveball instead. This enigmatic world is far less dense than it should be, clocking in at barely half the density of water. That's lighter than a frozen sponge, a cosmic contradiction for an object its size. So what's really going on beneath that dark, craterless surface? The leading theory is porosity. Varuna might be more empty space than substance. Picture a celestial snowball compacted just enough to hold its shape, but riddled with microscopic gaps and fractures. This wouldn't be entirely unprecedented. Some asteroids, like the rubble pile Itokawa, are known to be porous, but Varuna's sheer size makes this explanation radical. For an object nearly 700 kilometers wide to maintain such fragility, its interior would need to be a labyrinth of caverns and cracks, as if some ancient collision left it hollowed out like a broken eggshell. Supporting this idea are those bizarre thermal fluctuations we've seen. Pockets of warmth seeping through could imply voids where heat circulates unevenly, rather than a solid, uniform core. Yet there's an even wilder possibility. Varuna might be stuffed with exotic ices we've barely classified. Most density models assume standard water ice mixed with rock, but what if its composition leans heavily on molecular ices like methane clathrates or carbon dioxide hydrates? These substances form cage-like structures under pressure, trapping gas molecules in crystalline frameworks that are surprisingly light. If Varuna's interior is rich in these materials, its low density wouldn't be a sign of weakness, but of peculiar chemistry, like finding a boulder that floats because it's secretly made of pumice. The implications rewrite planetary formation theories. If Varuna is this porous, it challenges our understanding of how mid-sized Kuiper Belt objects hold together. Gravity should have compressed any voids over billions of years, yet here we are. One provocative solution: Varuna might be younger than we think. A catastrophic breakup and reaccumulation event, say a collision within the last billion years, could have left it loosely packed, its pieces never fully settling. Alternatively, its rapid spin might act like a centrifugal barrier, preventing compaction like clothes in a dryer that never quite tumble down. But the darkest horse in this race is the idea of subsurface volatiles. If Varuna hides reservoirs of methane or nitrogen gas beneath its crust, trapped by an overlying layer of less permeable ice, those pockets could artificially lower its overall density without requiring massive internal voids. It's the difference between weighing a sealed soda can versus an empty one. The mass might be similar, but the distribution tells a different story. On Earth, we see this in ice caps hiding subglacial lakes. On Varuna, the scales could be planetary. What makes this mystery so pivotal is what it reveals, or obscures, about the Kuiper Belt's diversity. If Varuna's feather-light density isn't unique, there could be an entire class of fluffball worlds out there defying our textbooks. Or worse, our measurements might be missing something fundamental, a hidden variable that's throwing all our calculations off. Every time we think we've pinned Varuna down, it slips through our fingers like dark matter, reminding us that the outer solar system is still, in so many ways, a realm of shadows and whispers. Even the dimmest stars in Earth's night sky hold steady, their flickers predictable. But Varuna, this distant rogue, refuses to play by the rules. Astronomers tracking its brightness over decades have recorded wild, erratic fluctuations. Not the gentle, rhythmic pulses of a rotating world, but jagged, unpredictable spikes and dips that defy conventional explanation. It's as if something on or around this icy enigma is playing tricks with the light, switching cosmic lamps on and off at random. The first suspect is Varuna's peculiar shape. Most rotating objects change brightness predictably as their uneven surfaces turn toward us. Think of how a tumbling potato might flash more light from its broad sides than its narrow ends. But Varuna's elongated form, combined with that dizzying 6-hour spin, creates a chaotic light curve. Some models suggest it might be pirouetting like a wobbly top, presenting irregular facets to Earth in ways that scramble any clear pattern. Throw in its probable rubble pile interior, where subtle shifts could alter its albedo distribution over time, and you have a recipe for optical chaos. Then there's the enigma of its surface. Varuna's coal-black crust is webbed with mystery compounds, tholins, cyanides, possibly even metal oxides, that don't reflect light uniformly. Imagine sunlight hitting a landscape where patches of fresh asphalt blend abruptly with polished obsidian and frost-covered tar. A single cryovolcanic eruption or landslide could expose brighter subsurface layers, causing temporary spikes before cosmic radiation darkens them again. Some researchers speculate about transient frost gases like nitrogen or carbon monoxide briefly escaping internal pockets to coat small areas before sublimating into space, creating fleeting reflective zones that vanish as quickly as they appeared. But the most unsettling theories look beyond Varuna itself. Could something in its environment be casting shadows? A diffuse ring system, too faint for direct detection, might occasionally drift between the distant sun and Varuna's surface, dimming its light in irregular cycles. Or perhaps clouds of dust and debris, leftover shrapnel from that hypothesized ancient collision, still linger in its orbital path, intercepting sunlight like interstellar smog. The Kuiper Belt is far from empty. We've detected micron-sized particles peppering spacecraft even in its sparsest regions. Varuna plowing through a denser patch could experience days-long dimming events, mimicking the brightness drops of faraway stars plagued by dust clouds. The wild card, external forces acting on Varuna's spin axis. Unlike Earth's stable rotation, nudged gently by the Moon's gravity, Varuna's lack of satellites leaves it vulnerable to subtle torques from passing objects or even galactic tides. A gradual shift in its axial tilt, something called polar wander, could suddenly expose previously hidden terrains to Earth's line of sight, rewriting its light curve overnight. We've seen this phenomenon on Mars and Pluto, but Varuna's rapid rotation might make these shifts more abrupt and dramatic, like a spinning top that abruptly starts wobbling in new directions. What makes these fluctuations so unnerving is what they imply about our ability to study distant worlds. If something as seemingly straightforward as brightness variations can resist explanation, how many other cosmic rules might be illusions? Varuna's capricious glow is more than a scientific puzzle, it's a lighthouse in the dark, reminding us that even in the orderly clockwork of the solar system, there's always room for chaos. Most worlds in the Kuiper Belt wear their chemistry like badges of honor. Pluto glistens with nitrogen glaciers, Eris sparkles with methane frost, even smaller bodies like Makemake cling to thin veneers of volatile ices that flash brilliantly in the distant sunlight. But Varuna, it stands apart, a stoic outlier cloaked in darkness, showing barely a trace of these ephemeral compounds. Where its cousins gleam with frozen gases, Varuna's surface is a chemical desert, and that absence speaks louder than any presence could. The first clue lies in volatility itself. Methane and nitrogen are cosmic fair weather friends, they stick around only when conditions are just right. Too close to the sun and they vaporize, too much heat and they escape into space. Varuna's orbit places it firmly in the zone where these ices should be stable, yet spectroscopic searches come up nearly empty. One explanation is that Varuna simply formed differently, perhaps in a region of the primordial solar nebula where these lightweight molecules were scarce, or where temperatures never dipped low enough to trap them in its bulk. Picture a world assembled from the cosmic equivalent of heavyweight building blocks, water, ice, rock, and complex organics, while its neighbors gorged on the volatile buffet around them. But there's a darker, more dynamic possibility. Varuna might have once been rich in these ices, only to have them stripped away. Its rapid rotation and low gravity create conditions perfect for atmospheric escape. Any gases that sublimate from its surface could be flung into space by centrifugal force before they have a chance to refreeze. Unlike Pluto or Eris, whose stronger gravity acts like a lid on a boiling pot, Varuna's feeble hold would let volatiles slip away like sand through fingers. Over billions of years, even a modest leak could drain its reserves entirely, leaving behind only the stubborn, heavier compounds we see today. Then there's the impact scenario. If Varuna truly is the survivor of a cataclysmic collision, the heat from that event could have baked away its volatile ices in one devastating pulse. Experiments show that when icy bodies collide, the energy released can flash heat surfaces to hundreds of degrees, enough to vaporize methane and nitrogen instantly, sending them rushing into space while only the toughest materials remain. It's the difference between tossing a snowball into a campfire versus a chunk of concrete. One vanishes in a puff of steam, the other endures. The most tantalizing and unsettling theory involves chemistry, not catastrophe. Varuna's dark, complex surface compounds might actually be the remains of its volatiles. When methane and nitrogen are bombarded by cosmic rays over eons, they don't just disappear, they transform. Through a process called radiolysis, these simple ices can polymerize into the very tholins and organic goo that now coat Varuna's exterior. In this light, its missing volatiles aren't gone at all. They've simply metamorphosed into something far stranger, like caterpillars dissolved into their chrysalides. The implications ripple beyond one oddball world. If Varuna lost its volatiles, it suggests even the Kuiper Belt's deep freeze isn't always cold enough to preserve the solar system's delicate chemistry. But if it never had them to begin with, then our models of planetary formation are missing a crucial variable, some mechanism that segregated ice giants from ice poppers in the nebula's earliest days. Either way, Varuna's barren face forces us to confront an uncomfortable truth. The outer solar system isn't just a museum of primordial ice. It's a graveyard of possibilities where what's missing matters as much as what remains. Most objects in the Kuiper Belt move like obedient dancers, their orbits neatly aligned with the solar system's flat, pancake-like plane. But Varuna, it pirouettes at a bizarre angle, its path tilted nearly 30 degrees off kilter, an orbital rebel refusing to follow the cosmic choreography. This isn't just a minor quirk, it's a fundamental anomaly that challenges our understanding of how the outer solar system settled into place. What could have knocked Varuna so dramatically off course? The prime suspect is gravitational chaos. In the early solar system, Neptune's migration, a slow outward drift triggered by interactions with leftover planetesimals, sent shockwaves through the Kuiper Belt. Smaller objects were flung like billiard balls, but Varuna's size should have made it resilient to such perturbations. Unless, of course, it had a fateful encounter with something far more massive. Some models suggest a close pass with a wandering rogue planet. A hypothetical world like Planet 9 could have yanked Varuna into its current crooked orbit. Picture a cosmic game of gravitational pinball, where a single near miss from a hidden heavyweight sent this icy world careening off the expected plane. Yet there's another, more violent explanation written in the geometry of its tilt. Varuna's orbital inclination matches patterns seen in collision debris, the telltale signature of an impact so catastrophic it didn't just reshape the object but altered its entire trajectory. Imagine two protoplanets slamming together in the outer solar system's infancy. The force wouldn't just shatter them, it could launch the fragments into wildly tilted orbits like sparks flying at odd angles from a grinding wheel. If Varuna is a surviving shard of such an impact, its odd orbital posture might be the scar of that ancient violence. The plot thickens when we consider resonance. Varuna's orbit appears locked in a subtle gravitational dance with Neptune, a 2 to 3 resonance, meaning it completes 2 orbits for every 3 of Neptune's. Normally, such relationships stabilize orbits, keeping them flat, but under rare conditions, resonance can actually amplify tilts over time, like a metronome gradually pushed off rhythm by an unseen hand. If Varuna slipped into this unstable resonance branch billions of years ago, the slow gravitational nudges from Neptune could have incrementally cranked its orbit askew. But the most tantalizing clue lies in Varuna's kinship with other tilted Kuiper Belt objects. It's not alone in its defiance. Several mid-sized worlds share similar orbital quirks, hinting at a shared origin story. Perhaps these outliers were once part of a now-vanished population, a swarm of objects shepherded into high-inclination orbits by a since-ejected planet or a long-forgotten gravitational disturbance. Their tilted paths might be fossils of a lost dynamical era when the outer solar system was still a shifting, chaotic frontier. What makes Varuna's slanted orbit so unsettling is what it implies about the solar system's adolescence. This isn't just one oddball world's rebellion. It's evidence that the Kuiper Belt's current orderly arrangement is a facade. Beneath the calm, the ghosts of ancient upheavals still linger, and Varuna, spinning silently on its tilted stage, is one of their loudest witnesses. Among the many puzzles Varuna presents, one of the most tantalizing is the whisper-thin enigma surrounding it. A ghostly, uncertain glow that some observations suggest might cling to this dark world like a wisp of cosmic breath. Unlike the definitive atmospheres of Pluto or Triton, this possible haze is so faint that astronomers still debate whether it's real or merely a trick of the light. Yet if it exists, it could rewrite what we know about how objects in the Kuiper Belt cling to or exhale gaseous veils. The first hints emerged from telescopic observations where Varuna appeared ever so slightly fuzzier than expected. Instead of a crisp point of reflected light, some datasets showed a barely there diffusion at its edges, as if sunlight were scattering through something more than empty space. The effect was subtle, so minor it could have been dismissed as noise or distortion from Earth's atmosphere, but the pattern persisted across multiple observations, always just on the edge of detectability. Could this be the signature of a transient atmosphere, flickering in and out of existence as Varuna's distance from the Sun changes? On warmer stretches of its elliptical orbit, frozen gases like nitrogen or carbon monoxide might briefly sublimate, creating a tenuous shroud that refreezes as it retreats into the cold. Then there's the dust hypothesis. Varuna's violent spin and oddly smooth surface suggest it could be shedding particles, tiny flecks of ice or carbon-rich material flung from its equator by centrifugal force. Over time, these particles might form a loose, orbiting halo, too sparse to see directly but dense enough to scatter sunlight. We've seen this elsewhere in the solar system. Saturn's E-ring is fed by geysers on Enceladus, while Jupiter's Gossamer rings are replenished by dust knocked off inner moons. If Varuna's surface is even minimally active, micro-eruptions or landslides could be feeding a similar, if far fainter, debris field. Yet the most perplexing possibility involves something entirely different: magnetism. While most small Kuiper Belt objects lack the internal dynamos to generate magnetic fields, Varuna's rapid rotation and rumored metallic content raise an eyebrow. Charged particles from the solar wind, deflected by even a weak magnetic bubble, could excite trace gases around the world, making them glow faintly like a shrunken, icy version of Earth's auroras. It's a long shot, but not impossible. The truth, as always with Varuna, may be stranger than speculation. That elusive glow, whether atmosphere, dust, or measurement error, remains a riddle wrapped in a shadow. But its mere possibility reminds us how much we still have to learn about the quiet, hidden dramas unfolding in the solar system's frozen fringe. In the Kuiper Belt, violence leaves lasting signatures when large objects collide. They often leave behind not just scars but entire families. Pluto has its retinue of smaller bodies tracing similar orbits. Haumea boasts a whole clan of fragments. Even mid-sized worlds like Orcus share their orbital space with collision-born kin. But Varuna, it drifts alone. Despite its size large enough to have surely suffered catastrophic impacts, no swarm of smaller objects accompanies it. This cosmic solitude isn't just unusual, it's a glaring anomaly that demands explanation. Where is Varuna's missing family, and what does their absence reveal about this world's turbulent past? One possibility is that its family did exist but didn't survive. Picture a colossal collision billions of years ago, one violent enough to shatter Varuna's precursor into fragments. In the chaotic aftermath, Neptune's gravitational influence could have scattered these pieces like billiard balls, ejecting them from the solar system entirely or sending them plummeting inward to become short-lived comets. The math supports this. Simulations show that objects in Varuna's orbital neighborhood are particularly vulnerable to Neptune's disruptive pull. Unlike Haumea's family, which clusters safely in a stable resonant zone, Varuna's kin might have been flung into oblivion before they could settle into detectable orbits. But there's a twist. Some collisions don't produce families at all, they consume them. If Varuna formed through a slow, grinding merger rather than a shattering impact, it could have gobbled up most of its potential debris, leaving almost nothing behind. Imagine two mid-sized protoplanets colliding at just the right speed, not fast enough to explode apart, but not so slow that they'd gently stick together. Instead, they'd shatter and coalesce like two cars in a head-on crash that weld together on impact while scattering only a handful of loose bolts. This might explain Varuna's bizarre shape, not a clean fragment, but a Frankenstein's monster of mangled remnants. The most tantalizing theory, though, involves time. Collisional families aren't permanent, they erode. Over billions of years, gravitational nudges from passing stars, the galactic tide, or even hypothetical rogue planets could have gradually dispersed Varuna's kin across such a wide volume of space that they're now indistinguishable from the general Kuiper Belt population. It's like trying to spot a single family reunion in a crowded city centuries after it began. The descendants are still there, but they've blended into the crowd. Some researchers suggest we have already spotted Varuna's lost siblings. They're just hiding in plain sight among the thousands of anonymous icy bodies catalogued by telescopes. Yet the absence of a family might not signal destruction but avoidance. Varuna's peculiar orbit, tilted steeply off the solar system's plane, could have kept it away from the busiest traffic lanes of the early Kuiper Belt. While other large objects jostled in the crowded midplane, Varuna's oblique path might have let it slip through the chaos unscathed, like a driver cruising smoothly in the emergency lane while a pileup unfolds in the main lanes. If so, its pristine solitude isn't a mystery, it's a testament to celestial navigation so perfect. It dodged the bullet of cosmic violence entirely. The implications stretch far beyond one world. If Varuna's missing family proves common among high-inclination objects, it could rewrite our understanding of the Kuiper Belt's evolution. Perhaps the outer solar system's history was shaped not just by collisions, but by avoidance, with the survivors being not the strongest but the stealthiest. Or maybe we're seeing the aftermath of a gravitational purge, where Neptune played the role of cosmic housecleaner, sweeping away the evidence of ancient crashes. Either way, Varuna's loneliness isn't just a curiosity. It's a silent witness to forces that shape the solar system in ways we're only beginning to decipher. In the monochrome expanse of the Kuiper Belt, where most icy worlds shimmer in shades of pale gray or faint blue, Varuna stands out like a cosmic ember, its surface glowing with an eerie reddish tint that defies easy explanation. It's not the blood-red hue of some extreme outer solar system outliers, nor the icy neutrality of its neighbors. Instead, it occupies a chromatic middle ground, a puzzle wrapped in wavelengths that whisper of complex chemistry unfolding in the darkness. What could paint a world this far from the sun in such unusual colors? The answer likely lies in tholins, those mysterious, complex organic molecules that form when simple ices like methane or nitrogen are bombarded by cosmic radiation over eons. Think of them as the cosmic equivalent of burnt toast. The longer and more intensely you expose organic material to energy, the darker and redder it becomes. On worlds like Pluto or Titan, tholins create vast rust-colored plains. But Varuna's coloration is more nuanced, suggesting either a different recipe or an interrupted cooking process. Its spectral signature hints at tholins that never fully matured, perhaps because Varuna's rapid rotation exposes its surface unevenly to radiation, leaving some regions lightly toasted while others remain pale. Then there's the wild card of cryovolcanism. If Varuna's interior occasionally oozes slushy brines onto its surface, these fluids could carry dissolved organic compounds that darken and redden when exposed to space. Picture a frozen lava flow, but instead of molten rock, it's a slurry of water, ammonia, and hydrocarbons seeping upward, then freezing into reddish stains against the primordial ice. Europa's chaotic terrain shows similar staining from subsurface chemistry, though on a vastly different scale. Varuna's weaker gravity and bizarre spin might create even more dramatic color variations, like a pot of cosmic tie-dye left half-finished. But the real curveball comes from Varuna's darkness. Most red objects in the solar system are also highly reflective, their colorful compounds gleaming in sunlight. Varuna, by contrast, is both red and dark, a combination so rare that some researchers speculate its surface might be layered like a terrible cosmic cake. Imagine a thin frosting of reddish tholins over a deeper, asphalt-black substrate of irradiated organics. Sunlight penetrating this top layer could get absorbed by the darkness beneath, muting the redness we'd normally expect. It's the difference between red paint on a white canvas versus red dye spilled on charcoal. The implications stretch beyond mere curiosity. Color is a fingerprint of chemistry, and Varuna's peculiar hue suggests it's been cooked differently than its Kuiper Belt cousins. Maybe it formed in a region of the primordial disk richer in certain hydrocarbons, or experienced a unique thermal history that paused its irradiation halfway. Every subtle shade in its spectrum is a clue not just about one odd world, but about the infinite variations hidden in the solar system's farthest reaches. In the end, Varuna's color isn't just a visual oddity. It's a silent testament to the diversity of processes that can unfold unseen in the eternal night beyond Neptune. In the orchestra of our solar system, many worlds sing with magnetic voices, Jupiter's deafening radio screams, Saturn's eerie whistles, even distant Uranus crackles with faint bursts of energy. But Varuna, it's stone silent, despite spinning faster than any object its size should. No radio emissions or magnetic fields have ever been detected from this icy enigma. It's as if someone hit the cosmic mute button, leaving astronomers to wonder, is Varuna's interior simply dead and inert, or are we just not listening closely enough? The absence of magnetic activity is particularly baffling when you consider Varuna's rapid rotation. Spinning once every 6 hours should, in theory, churn conductive materials inside the world, generating currents that produce detectable magnetic fields. We've seen this dynamo effect in smaller, slower objects. Jupiter's moon Ganymede, for instance, boasts a magnetic field despite being just slightly larger than Varuna. So why the silence? One possibility is that Varuna lacks the necessary ingredients for magnetic dynamos. Unlike Ganymede, which likely harbors a liquid saltwater ocean beneath its crust, Varuna's interior might be frozen solid, with no fluid layers to conduct electricity. Without that sloshing, conductive material, even rapid rotation wouldn't spark a magnetic field like trying to start a car with no battery. Yet there's a more unsettling explanation. Our instruments might be missing something. Detecting faint radio emissions from the Kuiper Belt is like trying to hear a whisper across a crowded stadium. Earth-based telescopes face interference from our planet's own magnetic field and the constant buzz of human radio transmissions. Even the most sensitive arrays, like the Very Large Array in New Mexico, struggle to pick up signals from objects as distant and dark as Varuna. Some researchers speculate that if Varuna does emit radio waves, they could be at frequencies we rarely monitor, or so weak they're drowned out by cosmic background noise. It's the celestial equivalent of searching for a single cricket's chirp in a thunderstorm. The wild card in this mystery is Varuna's rumored metallic core. If the collision that shaped it left behind a dense, iron-rich heart, that metal could theoretically generate a localized magnetic field, one too small or irregular for our current technology to detect. Mars offers a sobering precedent. While it lacks a global magnetic field like Earth's, pockets of magnetized rock prove it once had localized dynamo activity. Varuna's silence might not mean absence but fragmentation, a patchwork of weak, scattered magnetic zones that slip through our observational net. Then there's the time factor. Magnetic fields aren't necessarily permanent. Earth's own field fluctuates over millennia, and some moons exhibit sporadic activity tied to tidal stresses. If Varuna's internal heat has faded over billions of years, its dynamo could have sputtered out long ago, leaving behind only fossilized traces in its crust. Alternatively, its magnetism might cycle intermittently, flaring up during rare orbital alignments or internal shifts, meaning we've simply been listening at the wrong time. The implications ripple outward. If Varuna is truly inert, it suggests that size and spin alone aren't enough to power magnetic fields in the outer solar system. Internal composition is the real key. But if we're just missing its whispers, it means the Kuiper Belt could be humming with hidden activity, a chorus of faint signals waiting for more sensitive ears to hear them. Either way, Varuna's silence isn't empty. It's a question mark hanging over our understanding of how icy worlds live, die, and sometimes refuse to speak at all. In the grand timeline of our solar system, most Kuiper Belt objects are ancient archivists' frozen relics dating back 4.5 billion years, preserving the chaos of planetary birth in their icy cores. But Varuna, it's the cosmic equivalent of a teenager at a retirement party. Some measurements suggest this enigmatic world might be far younger than its neighbors, with surface characteristics hinting at an age just a fraction of the solar system's. If true, this anomaly shakes the foundations of what we thought we knew about the outer solar system's history. How could a world this size have formed so late in the game? And what processes could erase nearly all traces of its true antiquity? The first clue lies in Varuna's curiously smooth surface. Crater counts, the gold standard for dating celestial bodies, show far fewer impacts than expected for an object this old. While most Kuiper Belt worlds wear their cratered histories like badges of honor, Varuna's relatively unblemished face suggests either incredible luck in avoiding collisions or some mechanism actively erasing its scars. One compelling theory points to cryovolcanic resurfacing. Imagine sluggish eruptions of slushy brine seeping from Varuna's interior, spreading across its landscape like glacial paste, filling in craters over millennia. Even a trickle of geological activity, sustained over billions of years, could slowly heal its wounds, giving the illusion of youth. Europa and Enceladus demonstrate this principle on smaller scales, but Varuna's sheer size makes the idea radical. Then there's the possibility of a catastrophic makeover. If Varuna endured a colossal impact within the last billion years, say, a collision with another mid-sized Kuiper Belt object, the energy could have melted vast swaths of its surface, resetting its crater clock in one violent instant. Picture two ice worlds slamming together in slow motion, their surfaces flash, heating into temporary slush before refreezing into a smoother, younger-looking crust. This wouldn't just explain the missing craters, it could also account for Varuna's bizarre shape and spin, as if the impact didn't just resurface it but fundamentally reshaped it. But the plot thickens when we consider observational biases. Varuna's extreme darkness complicates crater detection. What looks like a smooth surface through telescopes might be pockmarked with subtle depressions hidden by its light-absorbing crust. It's like trying to count dimples on a black bowling ball under a flickering street lamp. Even the best data from Earth carries uncertainty, leaving room for error in age estimates. Some researchers argue that what we're seeing isn't youth at all, but an illusion created by Varuna's unique surface chemistry. Complex organic compounds might be masking crater rims, while its rapid spin could be redistributing impact debris in ways that flatten topography over time. The most unsettling hypothesis, Varuna might genuinely be younger, but not in the way we think. Rather than forming late, it could be a second-generation object assembled from the wreckage of older worlds. In this scenario, 2 or 3 mid-sized Kuiper Belt objects collided relatively recently, perhaps just a billion years ago, with their debris coalescing into the Varuna we see today. This would make it a planetary phoenix rising from the ashes of its predecessors with a fresh face and a turbulent past. Jupiter's asteroid belt offers a parallel. The family of fragments around the asteroid Charon are known to have formed in a collision just 5 million years ago, proving that cosmic recycling happens even in modern times. What makes this mystery so pivotal is what it implies about the Kuiper Belt's vitality. If Varuna is truly younger, it suggests the outer solar system isn't the stagnant graveyard we imagined, but a dynamic construction zone where worlds still remake themselves in slow motion. Every conflicting age estimate forces us to confront the limits of our cosmic chronometers, reminding us that in the darkness beyond Neptune, time doesn't always tick the way we expect. Deep in the Kuiper Belt's frozen wastes, where temperatures should be locked in permanent deep freeze, Varuna emits a thermal whisper that defies all expectations. Observations from infrared telescopes reveal heat signatures that don't align with the predictable cold of a world this distant and dark. While most objects at its orbit radiate a chill consistent with frigid, inert ice, Varuna's thermal profile flickers with subtle irregularities like a corpse with a faint, inexplicable pulse. What could be generating these anomalous warmth signatures in a place where the sun is little more than a bright star? The first clue lies beneath the surface. Most Kuiper Belt objects are thought to have exhausted their internal heat billions of years ago, their rocky cores no longer warmed by radioactive decay. But Varuna's rapid spin and distorted shape hint at residual energy still coursing through its veins. Imagine a thermos buried in snow. If it held even a trickle of warm liquid, that heat would seep outward unevenly, creating patches of slightly higher temperature. Similarly, traces of radioactive elements like potassium-40 or thorium in Varuna's core could still decay at a glacial pace, their faint energy warping the thermal equilibrium we'd expect. Given Varuna's likely porous structure, this warmth might circulate unpredictably through caverns and fractures, escaping in erratic bursts rather than a steady flow. Yet there's another possibility: Varuna's darkness might be tricking us. Its coal black surface absorbs sunlight far more efficiently than lighter-colored neighbors, trapping minuscule amounts of solar energy that most icy bodies would reflect away. Over millennia, this could create a thermal imbalance, with certain areas, particularly those facing the sun for prolonged periods, retaining just enough heat to skew global averages. Picture asphalt on a summer day. Even weak sunlight can make it scorching compared to surrounding concrete. On Varuna, where temperatures hover near absolute zero, even a few degrees of variance would stand out starkly against the cosmic background. The wild card: tidal forces from an unseen companion. While no moons have been confirmed around Varuna, the gravitational tug of a hidden satellite or the ghostly echoes of one long lost could flex its interior like putty, generating friction heat. We've seen this on a grand scale with Jupiter's moon Io, where tidal kneading fuels volcanic fury. On a smaller, colder world like Varuna, the effect would be subtler, perhaps just enough to create localized warm zones where internal ice softens into slush, disrupting thermal models. Then there's the chemistry angle. Varuna's surface is coated in exotic compounds, tholins, cyanides, possibly even metal oxides, that might behave unlike typical water ice under temperature fluctuations. Some laboratory experiments show that irradiated organic sludge can undergo exothermic reactions when exposed to cosmic rays, releasing tiny bursts of heat as molecular bonds reconfigure. If Varuna's crust is riddled with these materials, its surface could essentially be a low-grade chemical battery, discharging warmth in ways that baffle our assumptions about inert outer solar system objects. What makes these thermal quirks so unsettling is what they imply about the Kuiper Belt's dynamism. If Varuna isn't the frozen corpse we assumed, how many other distant worlds might harbor hidden warmth? In the unimaginable cold of deep space, even a few degrees of anomalous heat could signal unknown geologic processes or chemistry complex enough to blur the line between frozen wasteland and something far more intriguing. Varuna's mismatched warmth isn't just a scientific discrepancy, it's a crack in our understanding, letting in slivers of possibility where we expected only eternal frost. Every active world leaves traces: plumes from erupting geysers, clouds from sublimating ices, or the faint haze of dust kicked up by impacts. But Varuna, it drifts in suspiciously pristine emptiness, despite its rapid spin and irregular shape features that should send particles flying. No detectable dust halo surrounds it. This cosmic cleanliness is eerie, almost as if something is silently sweeping its vicinity clean. What force could be erasing the evidence of Varuna's activity before we even detect it? One explanation lies in scale. The Kuiper Belt is vast, and dust particles, even those ejected at high speeds, would disperse quickly across such distances. Unlike Saturn's rings, where debris is tightly confined by gravity, Varuna's potential dust would have no such constraints. A single grain launched from its equator could drift thousands of kilometers away within years, becoming lost in the background noise of the solar system's interplanetary dust cloud. It's like trying to spot a single snowflake in a blizzard from miles away. Not impossible, but staggeringly difficult with current technology. Then there's the solar wind's invisible broom. Charged particles streaming from the sun exert a gentle but relentless push on tiny dust grains, especially those with irregular shapes. Over time, this pressure can accelerate microscopic debris to escape velocity, flinging it out of the Kuiper Belt entirely. Varuna's darkness might worsen this effect. Its light-absorbing surface could theoretically charge nearby dust via static electricity, making it even more susceptible to solar wind ejection. Picture a world surrounded by an invisible force field, repelling its own debris before it can form a detectable cloud. But the most unsettling theory involves Varuna's hypothetical moons, or lack thereof. Without sizable satellites to gravitationally shepherd stray particles, any dust created by surface activity or collisions would have nothing to anchor it. On worlds like Pluto or Haumea, moons act as cosmic vacuums, capturing escaping material into rings or temporary atmospheres. Varuna's solitude leaves its dust homeless, condemned to drift away into the void. Some simulations suggest that if Varuna ever had a moon, its rapid spin could have torn the satellite apart long ago, creating a short-lived ring that dissipated before modern telescopes could spot it. Yet the absence of dust might not signal inactivity. It could hint at something stranger. If Varuna's surface is as resilient as its smooth, craterless appearance suggests, maybe it simply isn't shedding material the way most icy worlds do. Imagine a ball of tar left in the freezer, hard, unyielding, and unlikely to flake unless struck with tremendous force. If Varuna's crust is more asphalt than ice, even micrometeorite impacts might fail to dislodge meaningful debris, leaving its orbital neighborhood unnaturally spotless. The implications ripple beyond one oddball world. If dust-free zones like Varuna's are common, it could mean the outer solar system is far less cluttered than our models predict, or that we've underestimated the efficiency of cosmic cleaning mechanisms. Every undetected particle speaks to forces we're only beginning to measure, from magnetic fields we can't yet map to solar winds stronger than anticipated. Varuna's pristine emptiness isn't just a curiosity, it's a silent lesson in how much we still don't see, even when we're looking right at it. Most celestial bodies put on a predictable light show, brighten, dim, brighten again in steady rhythm as their surfaces rotate into view. But Varuna, its light curve reads like a cosmic fever dream, flickering erratically with patterns that refuse to follow the script. Even accounting for its bizarre shape and breakneck spin, the variations in its brightness twist and spike in ways no standard model can fully explain. It's as if something unseen is tampering with the lights, whether cloaked beneath its surface or lurking just beyond our gaze. The first clue lies in asymmetry. A smooth, symmetrical object, even one spinning wildly, should produce clean, repeating brightness peaks. Varuna's jagged light curve suggests something far rougher, a surface marred by extreme albedo variations, where patches darker than coal sit beside regions that might be bright as fresh snow. Picture sunlight glinting off a tumbling dumbbell dipped in ink, some facets catching the light while others swallow it whole. Yet even this doesn't fully account for the data. Some observations show brightness fluctuations that shift over time, as if the dark and light regions themselves are migrating or evolving. Could cryovolcanic surges be painting fresh frost over ancient tar pits? Or are we seeing the shadows of massive ice boulders rolling across fractured plains? Then there's the wild card of shape shifting. Most models assume Varuna's elongated form is static, but what if it's not? At its rotation speed, centrifugal forces alone could cause subtle deformations, stretching its equator outward while allowing the poles to rebound inward like a spinning water balloon. These minute changes, cycling with each rotation, might alter how light scatters off its surface. Add in the possibility of loose surface material sliding en masse from pole to equator under the relentless spin, and you have a world literally reshaping itself as we watch its light curve, the only breadcrumb trail left behind. But the most unsettling theories look beyond Varuna itself. Some astronomers have noted correlations between its oddest light curve anomalies and its orbital position, as if something in its environment periodically intervenes. Could a faint, undetected ring system cast irregular shadows as it tilts toward the sun? Or does Varuna plow through pockets of Kuiper Belt dust dense enough to veil its light momentarily? The strangest proposal involves interstellar interference, microscopic debris from passing comets or even dark matter streams warping the light on its way to Earth. It's a cosmic version of squinting through a frosted window, never quite sure if the blur is on the glass or in the yard beyond. What makes these flickers so tantalizing is what they imply about our methods. Light curves are supposed to be astronomy's Rosetta Stone's simple, decipherable records of a world's rotation and surface. Varuna's refusal to conform forces us to question whether we've been reading them wrong all along. Every aberrant spike and trough is a cipher waiting to be cracked, a whisper that this distant world might be hiding far more than just shadows. The Kuiper Belt is a cosmic nursery for comets. Icy wanderers like Halley and Hale-Bopp trace their origins back to this frozen realm, flung inward by gravitational nudges to become the spectacular visitors we see streaking across our skies. Most large Kuiper Belt objects leave behind a trail of such descendants. Pluto's kin pepper the inner solar system, and even smaller worlds like Haumea have been linked to comet families. Yet Varuna, despite its size and dynamic history, stands eerily absent from this lineage. Not a single comet bears its signature, no icy shard carries its chemical fingerprints. It's as if this world has been silently hoarding its fragments, refusing to share them with the cosmos. What could explain such cosmic selfishness? One theory points to Varuna's peculiar orbit, that steep 30-degree tilt off the solar system's plane. Most comets get their inward kicks from Neptune's gravity, but Neptune's influence is strongest along the ecliptic, the flat disk where planets orbit. Varuna's oblique path might keep it out of Neptune's reach, like a skater gliding along the edge of a rink while everyone else clusters at center ice. Without those gravitational assists, any debris knocked loose from Varuna would simply linger nearby or drift outward into the Oort cloud, never making the sunward journey that would mark it as a comet. Then there's the question of composition. Typical comets are rich in volatile ices, methane, nitrogen, carbon monoxide, that vaporize dramatically when warmed, creating those iconic glowing tails. But Varuna's surface appears stripped of these materials, coated instead in tougher, less volatile compounds like irradiated organics and metal oxides. If a chunk of Varuna did break free, it might lack the volatile fuels needed to become a proper comet. Instead of erupting into a brilliant display, it could drift sunward as a dark, inert lump, invisible to telescopes until it was nearly upon us. We might have already overlooked dozens of Varuna's offspring, mistaking them for ordinary asteroids, but the darkest possibility, Varuna might be a cosmic black hole for collisions. Its bizarre shape and rapid spin suggest a structure more fragile than most, a loosely packed rubble pile or a fractured iceberg held together by little more than gravity. If another object struck it, the impact might not launch debris outward so much as swallow it whole, the energy dissipating into Varuna's porous interior like a hammer striking wet sand. In this scenario, Varuna wouldn't spawn comets because collisions don't scatter its pieces, they bury them. Yet the absence might not be absolute. Some researchers speculate that Varuna's fragments could be hiding in plain sight among Jupiter's Trojans, those mysterious asteroids that lead and trail the giant planet in its orbit. Their reddish hues and unusual spectra match Varuna's better than any other Kuiper Belt object. If true, it would mean Varuna's children aren't missing, they've just been adopted by another family, their true origins obscured by the chaos of gravitational reshuffling over billions of years. The silence speaks volumes. If Varuna truly produces no comets, it challenges our understanding of how icy worlds contribute to the solar system's migration of volatiles. But if its offspring are merely disguised, waiting to be recognized, the revelation could rewrite the genealogy of every comet that's ever graced our skies. Either way, Varuna's vanishing act isn't just a puzzle, it's a reminder that the universe often hides its connections in the last places we think to look. Gravity should be straightforward, mass attracts mass, and the math rarely lies. But Varuna, it throws cosmic curveballs. When astronomers track the subtle tugs this distant world exerts on neighboring objects, the numbers don't add up. Its gravitational signature flickers with inconsistencies, as if something beneath that dark, craterless surface is warping the rules of physics itself. These anomalies aren't just academic quirks, they're breadcrumbs leading us toward one of the solar system's strangest interiors. First, consider the orbital dances of nearby Kuiper Belt objects. Just as Pluto's gravity herds its swarm of smaller companions into predictable paths, Varuna's mass should gently shepherd anything in its vicinity. Yet some of its neighbors trace wobbly, unstable orbits, their paths kinked by gravitational nudges too strong for Varuna's estimated size. It's like watching a marionette puppet jerked by invisible strings tied not to the puppeteer's hands, but to some unseen counterweight lurking just offstage. The most plausible explanation, Varuna's mass isn't distributed evenly. A dense metallic core offset from its center could create asymmetrical pulls, or vast subsurface caverns might leave pockets where gravity weakens unexpectedly. Picture a lopsided bowling ball, its weight shifted to one side, roll it, and it won't track straight no matter how you throw it. Then there's the speed anomaly. Varuna's rapid rotation should, by conventional models, gradually slow over time as tidal forces and internal friction sap its energy. But observations suggest it's spinning too steadily for its age, as if some hidden mechanism keeps rewinding its cosmic clock. One radical theory posits an internal gravitational battery, sloshing layers of dense brine or partially differentiated metals that redistribute mass as Varuna rotates, creating a self-sustaining dynamo effect. It's the celestial equivalent of a spinning dancer pulling their arms inward to accelerate. Only here, the limbs are subterranean rivers of molten salt or iron-rich slurries oozing through fractured ice. The darkest possibility, a buried relic from its violent past. If Varuna truly is the remnant of a colossal collision, its interior might resemble a shattered mirror, jagged fragments of a former core suspended in a matrix of porous ice, their uneven densities creating a patchwork gravity field. Computer simulations of such wrecked worlds show chaotic gravitational signatures eerily similar to Varuna's, with regions where gravity spikes or plunges without surface warning. Imagine walking across a frozen lake riddled with hidden fissures, your feet meeting alternate patches of thick ice and thin air. That's the kind of treacherous terrain these gravitational whispers suggest lies beneath Varuna's shell. Yet the most tantalizing clue comes from beyond Varuna itself. Several tiny Kuiper Belt objects have been spotted tracing odd, looping paths that shouldn't be stable unless an unseen mass anchors them. No telescope has spotted a moon or companion large enough to explain these patterns around Varuna, leaving astronomers to wonder, could there be a ghost in the machine? A cloud of ancient debris, a primordial black hole, or even a rogue clump of dark matter could theoretically lurk in its vicinity, bending gravity without emitting light. While these ideas flirt with the speculative, they underscore a humbling truth: the outer solar system may hide forces we've yet to name, let alone understand. What makes these anomalies so thrilling is their defiance. Every mismatched gravity reading is a crack in the facade of our planetary models, a reminder that even the coldest, darkest corners of space can harbor secrets hot enough to rewrite textbooks. Varuna's gravitational riddles don't just hint at what's beneath its surface, they challenge us to admit how much we still don't know about the invisible scaffolding of the universe itself. Collisions write the history of the solar system in scars and debris, yet Varuna's past violence lingers only in cryptic whispers. Unlike battered moons like Callisto or cratered worlds like Mercury, this distant enigma hides its ancient wounds too well. No sprawling impact basins fracture its dark plains, no obvious ejector fields fan across its terrain. But look closer, and the ghosts of cosmic crashes emerge in subtler ways, clues etched not in surface rock, but in the very bones of this strange world. The most damning evidence screams from Varuna's spin. That breakneck 6-hour rotation defies natural formation. No object this size should pirouette so recklessly without a catastrophic push. Computer simulations show such extreme spins almost always stem from gargantuan impacts, where glancing blows transfer angular momentum like a cue ball striking a planet-sized 8-ball. The numbers tell a chilling story. For Varuna to whirl this fast, it likely survived a collision with another body at least 1/10 its mass, a cataclysm violent enough to vaporize ice and shatter rock on planetary scales. The aftermath would have been apocalyptic, with debris swirling into temporary rings before either reaccreting or spiraling into the void. Then there's the haunting tilt of its axis. Varuna doesn't just spin rapidly, it does so at an odd angle, its poles skewed compared to its orbital plane. Such misalignments are textbook signatures of past trauma, like a boxer's crooked nose after one too many punches. Earth owes its own axial tilt to a primordial smash with Theia, the Mars-sized impactor that birthed our moon. Varuna's wonky orientation hints at a similar history, except without a lunar companion to bear witness. The crime scene lacks its most obvious exhibit. Surface chemistry adds another layer to the mystery. spectroscopy reveals bizarre concentrations of complex organics and possible metal oxides, materials that typically form under extreme heat and pressure. These could be the cosmic equivalent of blast residue-melted ices and vaporized rocks from the impact itself, splashed across Varuna's face before freezing into a permanent chemical tattoo. Laboratory experiments show similar compounds emerging when ice-rock mixtures are subjected to hypervelocity impacts, their molecular bonds shattered and reforged in the crucible of collision energy. Time is the great eraser here. In the Kuiper Belt's freeze-frame cold, geologic activity grinds nearly to a halt, yet even here, entropy works its magic. Micrometeorite rain over billions of years could have sanded down crater rims, while thermal cycling subtly rearranged surface ices like grains in an hourglass. Varuna's darkness plays accomplice too. Its light-absorbing crust masks topography that might otherwise betray ancient upheavals. What we're seeing isn't an unscarred world, but one where the wounds have faded into the equivalent of cosmic liver, spots visible only to the most sophisticated instruments. The most unsettling possibility, we might be staring at the wrong scale entirely. Some models suggest gargantuan impacts could shatter a world's interior without leaving dramatic surface marks, like a bell cracked by a hammer but still gleaming smooth. Varuna's porous structure and odd density variations hint at such hidden damage, a skeleton of fractures and voids lurking beneath an unblemished icy hide. If true, it means the scars aren't missing, they're just buried too deep for light to reach. What emerges is a detective story with half the pages ripped out. Varuna's past violence must have been spectacular, yet the evidence dissolves under scrutiny like fog in sunlight. This paradox forces a profound realization. In the outer solar system, even apocalypses can fade to invisibility, leaving behind only ghosts of momentum and whispers in the spin. The lack of obvious craters doesn't mean peace. It means we're decoding a universe where not all explosions leave visible craters, and not all survivors wear their scars where we can see them. The deeper we probe Varuna's mysteries, the more one unsettling question looms. Is this strange world truly alone in its oddities, or are we just blind to its kin? Every anomaly, its breakneck spin, its missing craters, its gravitational quirks paints a portrait of a cosmic misfit, an outlier defying the Kuiper Belt's norms. But outliers rarely exist in isolation. Nature tends to follow patterns, leaving us to wonder, is Varuna the last survivor of a vanished breed, or the first clue to a reality we've yet to grasp? Consider the possibility that Varuna isn't unique, just rare. The early solar system was a demolition derby of protoplanets, most of which were pulverized or swallowed by giants like Neptune. What if Varuna represents a nearly extinct class of worlds, fast-spinning, porous, and chemically bizarre, forged in a chaotic era when orbits were wild and collisions apocalyptic? We've glimpsed fragments of this lost population in other oddballs like Haumea, another rapidly rotating Kuiper Belt object with a distorted shape. But where Haumea left behind a family of debris as evidence, Varuna's kin might have been erased entirely, their fragments scattered beyond recognition. The universe is cruel to rarities. Without the safety of numbers, they vanish into silence. Yet there's another, more humbling take. Perhaps Varuna only seems unique because our tools are too blunt. The Kuiper Belt is vast, and our surveys have barely scratched its surface. For every Varuna we've spotted, there could be dozens more lurking in the observational shadows, their spins too fast or their surfaces too dark for current telescopes to catch. Think of the early 20th century when Pluto was thought to be a solitary oddball, until better technology revealed legions of icy worlds sharing its neighborhood. Our understanding of the outer solar system has always been limited by the faintness and distance of its inhabitants. Varuna's strangeness might not be a fluke, but a preview of the diversity we're only beginning to uncover. Then there's the cosmic wildcard. What if Varuna's anomalies aren't primordial at all, but the result of an unfathomably rare event? Astronomers once dismissed Jupiter's moon Europa as another frozen corpse until Voyager revealed its cracked, active shell, a transformation likely triggered by a singularly violent orbital resonance. Varuna could be the product of a similar one in a billion twist, a perfect storm of collisions, tidal heating, or interstellar interference that left it forever altered. In this light, its loneliness isn't statistical, it's historical, the sole heir to a trauma so specific that no other world bears its scars, but the most tantalizing answer. Varuna might not be alone, just hiding in plain sight. Its true siblings could be masquerading as ordinary Kuiper Belt objects, their similarities obscured by time. Imagine two trees growing from the same seed, one planted in fertile soil and the other in barren rock. Over centuries, they'd look nothing alike, yet share identical roots. Varuna's twins might have slowed their spins, lost their odd shapes, or been resurfaced by cryovolcanism, their kinship erased by evolution. Until we land a probe on its surface or discover another world with the same eerie fingerprint, we're left guessing whether its solitude is real or an illusion of incomplete data. The truth, as always in the outer darkness, lingers just beyond reach. Varuna's loneliness forces us to confront the limits of our cosmic senses and the nagging fear that the universe's strangest wonders might be the ones we haven't found yet. Whether it's a relic, a rebel, or a herald of hidden legions, this icy enigma reminds us that the solar system's story is still being written, in accents we're only starting to decipher. Varuna isn't just another icy rock in the Kuiper Belt. It's a cosmic riddle wrapped in shadow, a world that defies every expectation. From its breakneck 6-hour spin to its bizarrely smooth, craterless surface, this distant enigma refuses to fit into any neat scientific box. Why does it rotate faster than any object its size should? What hidden forces twisted it into that peculiar elongated shape? And how does a world so dark absorb nearly all sunlight, yet still flicker with unexplained thermal whispers? The deeper we look, the more questions pile up. Its missing moons, absent atmosphere, and gravitational anomalies suggest a history written in violence, cataclysmic collisions, chaotic orbits, or something even stranger we haven't yet imagined. Then there's the chemistry, a surface coated in compounds we barely recognize, from irradiated organics to possible metal oxides, as if Varuna was forged in a corner of the solar system unlike anywhere else. Its density hints at cavernous voids inside, while its tilted orbit and lack of a comet family suggest it might be an exile, a wanderer tossed into the Kuiper Belt by ancient gravitational upheavals. Even its age is a mystery. Is it a primordial relic or a second-generation world assembled from the wreckage of a forgotten collision? But here's the thrilling part: we're on the verge of answers. Upcoming missions like NASA, interstellar probe, and next-generation telescopes like the Vera C. Rubin Observatory could finally pierce Varuna's shadows, mapping its surface in unprecedented detail, or even sniffing out the composition of its ghostly haze. Every new observation peels back another layer, revealing just how much we've underestimated the outer solar system's complexity. Varuna isn't an outlier, it's a beacon, showing us how little we truly know about the frozen frontiers of our cosmic neighborhood. So, what's your take? Could Varuna's spin hint at a hidden ocean beneath its crust, or is it the scar of an ancient impact we'll never fully reconstruct? Might its darkness cloak active cryovolcanoes, or is its surface simply a cosmic graveyard of transformed ices? The comment section is your lab. Drop your wildest theories, your burning questions, and let's keep the conversation as alive as the mysteries themselves. Because one thing's certain, Varuna isn't done surprising us. Every clue we uncover only leads to deeper wonders, proving that even in the farthest reaches of our solar system, the universe still has stories